Okay, we're going to go through the first 4 problems here. Remember, find the absolute value or size of the complex number. All we're doing there is really just using our Pythagorean theorem. And we just need to plug it in. We get the square root of 5 squared plus the square root of negative 3 squared. And it's fine if you just go right to 5 squared plus 3 squared, because we know negative 3 squared is the same as 3 squared. So we get 25 plus 9, which gives us the square root of 34. And you want to make sure to break that down if possible. For this one, 34 is 2 times 17, so you can't break it down. So it's radical 34. So what that means is that this number, when graphed, is radical 34 units from the origin. So looking at letter B, from the very beginning, if you want to ignore the negative, because we know a negative 3 squared is the same as 3 squared, that is fine. And we get 9 plus 4, which is the square root of 13. 13 is a prime number. So again, we can just say that this number, negative 3 plus 2i, in the second quadrant is radical 13 units away from the origin. And then for C, some of you may just say right away, I know it's 4. And that's okay, because we know this is on an axis because there is no real part. You can still go through the process if you would like. 0 squared plus 4 squared gives you the square root of 4 squared, which is just 4. Okay? Again, on your test, if it says to show your work, you need to show your work. So please make sure you are prepared to do that. Now for the next ones, the first 3 are just simplifying the complex numbers. Remember, we can think about that in terms of rotations. So when you're thinking about the rotations, that means that if you're thinking about your real axes here and your imaginary, we're rotating it 14 90-degree rotations. Now, we don't want to have to count that, right? So a few things you can do is maybe you can do that in your head and figure out where you land. But what you want to do is kind of think about, what is I to the 14th equivalent to? The best way to do it is think 14 divided by 4, because every 4 values in your exponent, it's going to be 1 full rotation, right? And then it starts to repeat. So if we do 14 divided by 4, that's 3 times 4 is 12. Remainder 2. And so what this is telling us is that I to the 14th is equivalent to I squared. And we know that I squared is negative 1, which leaves us with negative 3. I to the 24th. Again, you can think about it. How many full rotations are we doing? 24 divided by 4 is 6. You get a remainder of 0. So that means that I to the 24th is equivalent to I to the 0, which is just 1. Anything to the 0 power is 1. And you can also think that we didn't rotate it at all, so we're starting just 1 in the positive real direction. I to the 101st. Again, we don't want to have to do 101 90-degree rotations. So let's divide by 4. We know that 4 goes into 125 times. So 25 times 4 is 100. You get a remainder of 1. So that means I to the 101st is equivalent to I to the 1st, and I to the 1st is just I. All right, the next ones, when we're looking at these, we're simplifying with negatives. Remember, this is the same thing as negative 1 times the square root of 64. We learned this unit, the square root of negative 1 is I. I times 8, we're going to write it as 8I. Do the same thing here. This equals the square root of negative 1 times the square root of 25 over the square root of 81. This leaves you with I. Square root of 25 is 5. Square root of 81 is 9. And we will write that as 5/9 I, or 5I over 9. And then for letter F, it's not a perfect square. So what you want to decide is what is the largest perfect square that goes into 243, and that is 81. Square root of -1 is I, square root of 81 is 9, square root of 3, can't do anything. So we will write this as 9 radical 3i. If you write it as 9i radical 3, that is fine. All right, number 3, we're going to graph 6 minus 7i. So we're going to go right 6, 1, 2, 3, 4, 5, 6, down 7, 1, 2, 3, 4, 5, 6, 7, and we graph a complex number from the origin, and we do that by sketching a vector. Okay, and it's okay if you do that as a solid or dotted. Now, it says to graph also I times that. So we learned that from the very beginning that I is just a rotation 90 degrees. So if you're starting with this vector, that means that we want to rotate this vector 90 degrees counterclockwise. So what you want to do is picture that 90 degree angle right here, and that's going to leave us with the vector 1, 2, 3, 4, 5, 6, 7, up 1, 2, 3, 4, 5, 6. And that will leave us with the point 7 plus 6i. Okay, so again, we got that by doing the 90 degree rotation because we're multiplying by I to the first power. We can show this algebraically by distributing our I. Leaves us with 6i minus 7i squared. And we know that I squared, we can plug in -1, which gives us 7 plus 6i, and it checks. All right, the next is on the complex plane is showing a sum of two complex numbers. And I will start with our first one, which is 2 plus 4i. So the way that we show this, we start at the origin, we go right 2, up 1, 2, 3, 4. So we're going positive in the real, positive in the complex, and we do a dotted line, show that first number with a vector. Now from there, we're going to kind of pretend that that's our new origin, and then we're going to plot -8, -7, and we're going to do that by going left 8 from there. 1, 2, 3, 4, 5, 6, 7, 8, and then we're going to go down 7. 1, 2, 3, 4, 5, 6, 7. And we're going to connect the end of the purple vector to that point. Okay, and then your final answer goes from the origin to where that point, the blue one, ended. Okay, so the red one is our answer. That's what we got from our sum. And if you count it, it's left 1, 2, 3, 4, 5, 6, down 1, 2, 3. And we can confirm that algebraically up here by adding our like terms. You add your reals. 2 plus -8 is -6. You add your complex parts. 4 plus -7 is -3i, and that does check. All right, so those are the first 4 problems of the review.